Last few lectures we've been learning how to use truth tables in order to determine when a compound proposition is true or false. That is to say, in order to determine all the conditions under which a compound proposition is either true or false. Today we're going to look at properties of both individual propositions, and also we're going to look at relationships that hold between multiple compound propositions. So beginning with looking at properties of individual propositions, there are going to be a number of important features or properties that individual propositions might have. And some of these I actually talked about in the answer to the last homework assignment, but I'm going to go a little bit in more detail today. We're going to begin by talking about what we call contingent propositions or contingent statements. And these are the majority of what we've seen so far. Basically, a proposition is a contingent proposition if it is more or less just true sometimes and false sometimes. We describe that proposition as being a contingent proposition. Now, there are other kinds of propositions, however, and probably contingent statements are the ones we're most familiar with. Most things that we experience in life, maybe sometimes they're true and sometimes they're false. And even propositions that are true quite often have the potential to become false at a later time. For instance, if I say, it is raining, it might be true right now, but then if I utter it once the rain stops and I say, it is raining, well, then it's false at that point. Or I say, this food is good. Well, sometimes that's true and maybe sometimes that's false. Maybe that's not the best one to use because that's subjective. Or if I say, I don't know, the cat weighs 5 pounds. Well, maybe that statement is sometimes true and maybe sometimes it's false, just depending on which cat you're talking about. I'd say probably the majority of statements we encounter are, they have the potential to be true or false, just depending on the circumstances and occasion. There are other statements, however, which are timelessly true. They're just always true no matter what. And these statements we call tautologies. These are statements which are just, you might say, necessarily true. That's the way sometimes it's expressed, or timelessly true. I don't quite like putting it saying timelessly true because that can be a little bit misleading. But think about a statement such as, I mentioned this one last class, but I think in the answer to the last homework assignment, death is the #1 killer of men, women, and children each year. Well, that's just, it's impossible for that to be false because death obviously is the killer. It's just that's kind of a silly statement. Or if you were to say, you might have heard someone say, wherever you go, there you are. All right, that's a tautology. In logic, we typically focus when we're talking about tautologies on the logical form of a proposition. And take a proposition like this: P if and only if P. P if and only if P. Well, let's look at this for a second and put this on a truth table. So when is a biconditional true? Well, a biconditional is true whenever both parts of, or both propositions in the biconditional are true, and a biconditional is false if both propositions are false. So look at this right here. True and true, so the biconditional is true, false and false, so it's true. So in logic, the way we define tautology is not just timelessly true or necessarily true, though saying necessarily true is maybe not the worst way to say it. But basically when there's nothing but truth assignment, or let me rephrase that, in all rows of the main connective, we assign it the value of true. So it wouldn't matter if it's 2 rows like this or if it was 10,000. If they're all true, we say that proposition is a tautology. Now, as it turns out, we're not going to use tautologies too much in this class. If this were an extra semester long, or if the class were just structured differently, believe it or not, tautologies have an important role to play in what are called logical proofs. We're not going to get into proofs because I just find that they're not something that the majority of people need to learn. If you were going into computer programming and you wanted to spend a class in just symbolic logic, these would become very important at that point. But for us, it's sufficient just to know what a tautology is. In addition to saying that some statements are always true, there are also some statements that are always false, no matter what. So I think I gave this example in class in the last homework assignment too. saying, I can't speak a single sentence of English. If someone were to say, I can't speak a single sentence of English, that sentence is just, it undermines itself because you just did it. All right, you're contradicting yourself. And when we talk about this in logic, again, we can express it in terms of truth tables, but if you were to assign false for every row under the main connective, if every single row is assigned false under the main connective, then that statement is a self-contradiction. So we look at an example like this, P and not P. We could go through the whole rigmarole if you want, but hopefully at this point you get a sense of how this goes. But we have the true here and false here, and the conjunction is false. The conjunction is only true if both of the conjuncts are true. False and true, false. So you see right here under the main connective, this is assigned a value of false for all of these. And again, it wouldn't matter if it were 2 rows or if it were 10 billion rows. If every single one of them is false, then it is a self-contradiction. Now, I should go back a slide really quickly and point out these two properties, or these three, contingency, tautology, and self-contradiction, these are properties of individual propositions, right? Individual propositions. I guess I should have given you an example of a contingent statement, but actually all the ones we've been looking at so far have been contingent. If I just did P and Q, that's a contingent statement because that's, sometimes true and sometimes false. So that's a contingent statement. But notice that what we're talking about here with contingency, tautology, and self-contradiction, we're talking about properties of singular or individual propositions, P and Q, P if and only if P, P and not P. We're asking, are these compound propositions? What feature do they have? Is this compound proposition contingent, a tautology, a self-contradiction? All right, that's going to be important because later on we're going to be comparing propositions, compound propositions to one another. But right now we're focused on, as it says up here, individual propositions. Now, so far, the examples I've given you have been pretty straightforward, but sometimes these can be really complicated. And I want you to look at this right here, and we're focused on this entire compound proposition. Is this a contingent one? Is it a tautology? Or is it a self-contradiction? Well, we have to fill out a truth table in order to figure this out. I mean, I can't look at this and just tell from knowing, just have an intuitive grasp. So just bear with me here. But we have our old trusty truth table. Now, if we were doing this and kind of dotting all our I's and crossing all our T's, I would have so let's go through the 3 steps. But at this point, hopefully you have the 3 steps, the 3-step method somewhat down. But we fill in our truth table here. Notice I have a column for each atomic proposition and each connective over here. And I have 2 columns for my P's and Q's. And just like always, we fill these in, true, true, false, false, true, false, and then we transfer those values over. Now the next thing we're going to want to do is we're going to want to, or actually we should have done this already, figure out what our main connective is. And our main connective, hopefully you can see, is this right here, this conjunction. That is our main connective. So we're going to fill in its truth value last. And we're going to begin by filling in the truth values of the other connectives, starting with connectives of least scope. Now, we can start wherever we want, but we could start right here within these parentheses, or we could start within these parentheses. And what I'm going to do is I'm going to start us off, there we go. I'm going to start off by looking at the very first set, just because, it comes first. There's really no logical reason. And we're trying to figure out the truth value of this conditional. So we're using P and Q, and we have true, true, so this would be true, true, false. And as you note at this point, that's false. False, true, well, that's true. And this right here is also true. So we finish that, and we're going to move on to the second parentheses over here. We're going to do this one. And here we have 2 connectives. We have and we have not. Well, we have to do the negation first because that has the least scope. So let's do that. We're negating, as you can see right here, we're negating Q, so it's going to be false, true, false, true. So that's how we fill in this column. Then what we're going to do is we're going to come over here and we're going to do the and. And we have, here again, we're going to do the and, draw an arrow here. True, false, this is going to be false. True, true, this is going to be true. False, false, this is going to be false. False, true, this is going to be false. Now we've done everything, and so we're going to lastly come to our main connective, the conjunction right here. So let's do that. And as you know, conjunction is only true if both conjuncts are true. And again, your conjuncts here is this compound proposition and this compound proposition. Those are your two conjuncts. True and false. False. True, false and true. False. True and false. False. True and false. False. So look at this column right here in the center. Notice that every assignment is false. And for that reason, this is a I'm not going to write this whole thing out because this is a self-contradiction. This statement right here, that compound proposition, that's a self-contradiction. It's contradicting itself. It's not true under any assignment of truth value for P and Q. So pretty fascinating stuff, huh, boys and girls? All right, well, let's look at one more. We have if P, then P or Q. I think we saw this one last time, one similar to it, but we'd fill in our truth table just like before, put in all our truth values, and then what we want to do is we want to figure out what our main connective is. And hopefully you can tell that this right here, the conditional, is our main connective. So what we're going to do is we're going to begin filling in our truth table with the filling out the connective of least scope, which is this disjunction right here. So let's do that. We have true and true. That means, let me get my pen here. This is going to be true. True and false. True. False and true. True. And then false and false. False. So we fill that column in. And now we come to our main connective. And notice here, P is our antecedent and P or Q is our consequent. And so the conditional is only false when the antecedent is true and the consequent is false. That's the only time it's false. So true and true. True. True and true. True. False and true. Well, that's true because the only time it's false is up here. False and false, true. So notice what our main connective is. Our main connective here is true in every instance. This proposition right here is a tautology. It's true no matter what. It can never be false. It's impossible for this proposition to be false. So I'll give you these as examples so that you can see that tautology, self-contradictions, they're not always immediately obvious, and so you do have to do these truth tables in order to know, are you dealing with a tautology or a self-contradiction? Now, I want to talk about, we just got done talking about two properties of individual propositions, and I want to move on to talk about properties or relationships between propositions, and I have to say, and probably shouldn't, but I find this section to be a little more interesting and a little more important because what you find a lot of times when you're studying logic, or let's not even doing logic, but you're just engaging in an argument with someone, or you're trying to understand someone's point of view, you a lot of times will hear a person express something one way, and you're like, wait, is that consistent with what you said over here? And this is why studying these relationships between propositions can be important, because people can say the same thing in different words. You can use and not to say something that you might say with or and not. You can also express something using a conditional, and that be expressing the same thing as something that was said using negation and disjunction. So there are different ways to say the same thing. And we're going to begin excuse me, by talking about when two propositions are consistent. And basically, and you have to really, this is something also I want to highlight here, you really have to pay attention to these definitions. These definitions are very, very important. So two propositions are consistent when they are true in at least one of the same row. So two propositions are consistent if they are true in at least one of the same row. So we're looking now at two propositions. I want to be clear about this. We're not just looking at one. We're looking at this proposition right here and P and Q. And so we want to compare these two and say, hey, are these propositions, do they have the same truth value or a different truth value or what? So we're going to be comparing these. And so the first one we're looking at is P or P and not Q. So let's just say I go ahead and I construct a truth table for this. And here it is. I'm just going to skip through all the steps because at this point you've seen enough of these. Hopefully I don't need to walk you through it. But here is the truth table for it. And again, this right here, this disjunction is the main connective. And so you see here that this is, in the row 1 is true, row 2 is true, row 3 is false, and in row 4 it's true. And then here's a truth table for our other proposition, P and Q. And again, I have highlighted in red when it's false and green when it's true. And what we're doing is we're comparing these. And I want you to notice there's some similarities and dissimilarities. For instance, row 4, this proposition on the left is true, whereas this one is false. And this one right here in row 3 is false, and this one is false. So they're the same there. So they're different in 4, they're the same in 3, they're different in 2. But consistency is what we're interested in here, and they are consistent because of row number 1. This is what makes them consistent. For two propositions to be consistent, they don't have to have, whoa, sorry, I clicked too soon. For two propositions to be consistent, they don't have to have all the same truth values. All that matters for consistency is that they are true in at least one row that is the same. As long as they both have an assigned value of true and at least one row that's the same, they are consistent. Consistent does not mean equivalent. Those I'll mention later. If two propositions are equivalent, they're also consistent. But just because two propositions are consistent does not make them equivalent. What makes two propositions consistent, and I'm sorry I'm beating a dead horse here, but it's merely that they are true at least sometime, right? There's at least one assignment of truth in which they have the same truth value. So that's what consistency means. So that's consistent. Now there's also what we call inconsistency. And two propositions are inconsistent when they are not true in any of the same rows. So we're looking now at these two propositions right here. We're looking at P if and only if Q and P and not Q. And we're going to construct truth tables for those, and I'm just going to go ahead and put them up. But P if and only if Q, here's our first proposition, and here's our second, P and not Q. And I've just gone ahead and I've filled these out, so hopefully you can just take my word for it. But I want you to look here. In row number 1, this is true, and this one's false. In row number 2, this one's false, and this one's true. In row number 3, hey, look, they actually are the same. They're both false, but it doesn't really matter. And then this row right here, this one's true, and this one's false. So they do have some similarity in row 3. Everything else is completely opposite. But what's critical for understanding, what makes these inconsistent is the fact that they are not true in any of the same rows. There's no row in which this is true and this one's true. There's not a single one. We don't care about falsity because here's why it's so important to pay attention to the definitions. Go back a slide, if computer will assist me. When two statements are not true in any of the same rows. Notice how we're defining inconsistency. They are not true in any of the same rows. Inconsistent propositions don't have to have the same truth value as each other. They don't have to both be false. If I don't know, just hypothetically, let's just say that this one right here in row 3 was true. Let's just say. It doesn't matter if they have the opposite truth values. They may not. as long as they are not true in any of the same rows, they are not consistent. If, for instance, now this is kind of interesting, if all of these were false and all of these were false, these would still be inconsistent. They would be inconsistent because of how inconsistency is defined, which is not true in any of the same rows. Even if, like I said, both propositions were entirely false, they would still be inconsistent according to this definition of inconsistency. So that is consistent and inconsistent. Now I want to talk about equivalency. And this is actually of all the, well, not of all of them, but this is one of the relationships between propositions that I actually find extremely helpful to understand and know. So this one's important to me. I don't know if that matters to you or not, but I do think this is a quite helpful one. And it's just kind of fascinating to me to see how you can say something differently, and yet those two propositions have the same truth values. And I'm going to give you a few examples of this right here. So look at this right here. We're going to go do both of these, but if P then Q and not P or Q. And let's construct our truth tables, and we can go ahead and see these. So I've just gone ahead and taken the liberty, and this truth table right here, well, this is just the truth table for conditional. So nothing terribly fancy or out of the ordinary there. This one over here, I had to do a little bit more work. You see here we're using the not P, but I constructed the truth table for it. And we're comparing these two. And look at it. True, true. False, false. True, 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 true. So you notice here that these are equivalent propositions. These are equivalent. And the reason they are equivalent is because they have the same truth value in every single column. I'm sorry, every single row. And again, we're looking at the main connectives. We're comparing the main connectives. So these propositions are equivalent. Let's do another side-by-side comparison of the other proposition I had listed, if it'll come up here. And let's look at this one. Not P and Q. Right? We're saying, I'm trying to think of an example here. It is not the case that John and Sarah are going. Not P and Q. And then John is not going or Sarah is not going. Right? These are saying the exact same thing. Or maybe I should have said the first one a little differently. It is not true that both John and Sarah are going. I'm sorry, that's what I meant to say. So it is not true that both John and Sarah are going. It's the same thing as saying John is not going or Sarah is not going. And you can see here, we can just do a side-by-side comparison. This is false, true, 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 false, true, true, true. Like I said, I went ahead and filled these charts out for you so we didn't have to, go. It's kind of a tedious process to go through it every time and fill out the truth tables every single time, especially when they're quite simple like this. But hopefully you can see here, and this is what I was saying, why this is interesting, is because over here we're expressing this proposition right here in terms of negation and conjunction. Over here we're doing it in terms of negation and disjunction. But these two, here we go, use our other symbol, are equivalent to one another. These are equivalent. And you find quite often that people will say, something using disjunction. Say, I think the example I gave a long time ago was something to the effect of, it was one of the class exercises, like, I'm not going to Iowa I'm not going to Iowa or Arizona. I'm not going to Iowa or Arizona. Well, that's just to say the same as saying, I am not going to Iowa and I am not going to Arizona. In other words, this right here, we'll use, that's supposed to be an I or a, is the same thing as saying not a, I and not a. All right? These propositions right here, these are equivalent to one another. So, and it's just kind of interesting to note that, like I've said multiple times a day, you'd probably be drunk now if you were taking a shot every time I said this. You can say the same thing, but express it using different connectives. Actually, I said it a little differently that time, so you'll have to wait till next time to take your shot of Jack. All right. Lastly, contradiction. Now, I want to be clear here. When we talk about contradiction, this is not the same as self-contradiction. An individual proposition, a singular proposition, it creates a self-contradiction when it's never true. A contradiction, by comparison, is a relationship that exists between two separate propositions. So, for instance, right here, this proposition and this proposition, as we're going to see, these are contradictory. And what is a contradiction? Is when the statements have the opposite truth value. They have to have opposite truth value for every row of their truth table. So let's look at these right here. So we have not P or Q, and we have P and some reason I have a parenthesis here, but P and not Q. And notice here, this one's true and this one's false. This one's false and this one's true. This one's true and this one's false. This one's true and this one's false. They have the opposite truth value in every single row. And for that reason, they contradict each other. They contradict each other. Now, I want to point out something here is that all statements that are contradictory are inconsistent, but not all statements that are inconsistent are contradictory, right? If you recall, when we looked at our definition of inconsistent, to be inconsistent just means that the two propositions, they're never true in the same row, which is actually going on here. They're never true in the same row. But contradiction, you might say, is a special kind of inconsistency. It's a specific type. And for contradiction, the two propositions actually have the complete opposite truth value. Again, for statements that are inconsistent, you don't have to necessarily have opposite truth value. Like, for instance, if this one right here had been false in every single row, these statements would then be inconsistent because they wouldn't be true in any single row. But they wouldn't be contradictory because they would both be false in row number 2. All right? So they wouldn't be contradictory because they wouldn't be polar opposites of one another. So contradiction, like I said, is a special kind of inconsistency where the truth values are complete opposite in each row of assignment. Okay, so this lesson is actually probably one of the shorter ones, but I'm going to assign you guys some problems, and for these problems what I want you to do is you'll read the instructions, but basically you're going to go through and you're going to figure out whether or not propositions are contingent, tautology, self-contradiction, and also you're going to look at and construct truth tables for two propositions and try to figure out the relationship between them. Are they consistent or inconsistent? Are they contradictory or are they equivalent? So if you have any questions, please feel free to email me.